Great. So I'm John Klein, back to talk with you about runtime assurance for big data systems. So some terminology. Assurance, as Kevin said yesterday in the introduction, confidence in the capabilities that we're delivering. And what's this about runtime, right? Because Kevin talked yesterday about wanting to build this in, do it up front. Well, in big data systems in particular, and many other kinds of systems, design time approaches like what Sagar and Peter and my other colleagues have been talking about are necessary but not sufficient. We do our best to design these systems, but then we turn them loose in the wild, and they get data from sources that aren't all under their control, so you can get more and different data than what you expected. Your users, the mission changes, they start running different analytics, different workloads maybe than what you expected. You're running this in a shared infrastructure that's very hard to model up front. So we're doing approximate models. And so the real world is a challenge. And so what we need to do is monitor these systems in their runtime environment, understand how they're operating. Are we still within the design envelope that we targeted? And if not, how far out are we, and do we need to start worrying? So our work this year has been on how do we collect measurements from a running system, and future work is how do we use that to assess the system health, predict, and diagnose. Why is this a hard problem? Well, when we talk about big data systems, the scale we're talking about is maybe thousands of nodes, thousands of individual servers running in a data center. Maybe millions of time series measurements if we start instrumenting this system and trying to understand how it works. So efficiency is critical, and we need to do some things other than just manual brute force. The other thing, and this is in particular with big data systems, is the frameworks that we use have a lot of resiliency and redundancy built in. Data is replicated, there's redundant processing elements, and so looking at the status of an individual server doesn't necessarily tell us anything. We can lose a lot of individual servers and our system will still be operating and delivering its capabilities in a good way. And so looking at sort of detailed status isn't going to help. We need to aggregate this together to get a view of how is the system really operating in its environment. So our approach, scale drives us to automation, obviously. Right? If we're going to talk about thousands of nodes, we want to generate the monitors automatically, we want to insert them automatically, we want to start aggregating the data. There's another dimension of scale that I don't have on the slide, and it maybe gets to this last question. We've got to scale to work with the skills that we have, right? If we want this to be adopted and usable, it's got to scale out to the people that we have, and it's got to be usable by average architects. So that's part of our solution. And so the question is, how are we going to automate this? What are we going to use as a model? What's going to give us some leverage that will let us start to help us think about how can we build models to automate? And so for that, we look at architecture styles. Styles are patterns. And these provide some abstractions and constraints that allow us to start building some efficient models. So a pattern or style tells us of particular types of elements, how they're arranged. And then we've done some extensions to that, a new contribution by attaching information about system health into the pattern. And that tells us what do we need to measure. So for a particular pattern for a big data system, something like MapReduce or Ingest pipeline, parts of our system, we can look at the pattern and it will tell us what do we need to measure, where do we need to measure it, and how do we pull those measurements together to get some overall assessment as to whether this part of our system is working correctly. So our approach is this, and let me start at the end and work backwards in explaining it. So we want to start by, as we said, automating the generation and deployment of monitors, and that's the part down here at the bottom. We do that using a description of the system architecture. That description of the system architecture is built by the architect using some style information that provides a meta model. If you're into model-driven engineering, the meta model is the constraints for the model that you're building. And then the meta models or the styles are built by experts and researchers. So there is some heavy lifting that has to get done here. So let's explain it, the details and the results, sort of working from the top down now. In terms of style definitions, anyway. Yes, yeah, good. Yeah, so this is actually the hidden incentive to come see the poster. Architecture styles or patterns. What you would see here are things that you might recognize if you work in the big data world. Things, as I said, like MapReduce, ingest pipeline, maybe some more esoteric things if you're a real big data geek, Lambda style, publish, subscribe streams. These are little chunks of design that architects use in order to build their system. And so we have extended the usual definition of a style, which typically says these are the types of components, these are how they're arranged, with information about measurement. So here I'm looking at the ingest pipeline. This is the part of the system that acquires data from the outside world. And what we've got here is some types of components. There's an adapter and a transformer and a writer. And then we've extended that with health information. So what does it look like when this thing is running correctly? If we're within our design envelope and it's operating as intended, well, it's going to keep up with incoming data. And how do we measure that? Well, if we go to the input source adapter, we measure the number of records coming in, and we go to the writer and we look at how many data elements are being written into each namespace. And maybe we want to do some application-specific peg counts. And we're going to then collect and aggregate this information that will tell us that this part of our system is operating as intended. This particular meta model came from some discussions actually that we had with a particular agency where they were running their big data system looking at information from different regions and found that there was no activity in one region. It had been running for several months. It turned out when they dug into it that it wasn't because there was no activity in that region, it was because they never acquired the data. Their source adapter for that was broken. And that's, I think, well, two things. One is it's an informative example. The other is it tells you these are big systems. And if you try to tackle these problems manually, you're going to miss things. And so part of this automation is systematizing the insertion so that things don't get missed. So the next piece is actually creating system architectures. And for this, we used the Acme Architecture Description Language Framework. This was developed at the CMU School of Computer Science. And it allows an architect to use a familiar environment, the Eclipse environment, to create a model of their system. This is a model of a MapReduce system that does Twitter sentiment analysis. So you can see some data sources. There's a mapper, there's a reducer, scheduler. The key things are that the architect builds this system model, and he or she builds it using component types that are defined by the style. So it's a constrained sort of thing. If you want to build a MapReduce piece of your architecture, there are only certain types of components. You can think of it as you've only got certain Lego blocks that you can build with. You can build a bunch of different things with those blocks, but you're constrained. Finally, the automation of the generation and insertion of the monitors. This piece of work was done. We collaborated with the School of Computer Science, the Master's Software and Engineering program, and had a student group do work. Here they focused on measuring and aggregating measurements for the persistence layer in a big data system. Many big data systems have multiple data stores for different types of data. We're going to put documents in one store. We're going to put metadata in another store. We're going to put our indexes in a third store. And we want to be able to treat these holistically when we assess the performance of the system. And so this is work that they did on generating and inserting monitors and then aggregating that data across multiple different types of data stores. Key things here are that it's model driven. If you could read the text in that yellow box, it would say the model has changed. And originally, every time the model changed, we automatically updated the visualization. We found that was kind of cumbersome, and so after the model changed, you could click the button to manually update it. That way it wasn't running out underneath you. And it was multiple databases that they were pulling data together from and visualizing here. So our results, we set out to say, can we solve this problem? And the answer is yes. We've demonstrated that we can use architecture styles to automate this generation. We can do it at scale. The limitations, there's always limitations in research. It was manually integrated, so the pieces were performed separately and tied together by people. Our monitor generation was a little weak. We focused only on the persistent store layer. And so that leads us to some future work. A couple areas. One would be looking at some particular types of systems. For example, the Naval Tactical Cloud uses a particular framework called Apache Storm. And that's all written in Java. Java gives us some nice tools to be able to go in to an existing system and transparently add capability. So could we take an existing instance of this system and add the monitoring? There's always more work to be done in extending and automating. But then the last piece, as I mentioned, our focus this year was on collecting and acquiring data. And the next step after that is to start using that information to assess, predict, and diagnose the health of our systems.